Hello, thank you, Dr. McMahon, for that introduction. My name is Kaustubh, and I am part of the AV3 group. I lead all the mechanical engineering related stuff as we are building a drone. And um, we also have Claire Lau with us here. Claire, if you want to introduce yourself.
Yeah, my name is Claire Liao, and I am part of the mechanical team of the AV3 group.
Yeah. So kind of the main gist of the group is that we use autonomous drones for terrain mapping and route creation, along with optimization to enhance search and rescue operations. So the basic premise of our group is to create different travel routes after, say, a natural disaster happens. So maybe an earthquake or a flood, and then we would send our autonomous drone out to take images of said terrain and use backhand models to kind of figure out the most optimized route. So let's continue. Also, a quick disclaimer, there are no members who actually do work on the software here, so bear with us for any uh, technical errors that we may make. All right, Claire, you can take this.
So I want everyone to imagine that they are part of a search and rescue operation team. And in order to find the person that is missing inside of anywhere, um, they'll encounter a couple of issues. Firstly, a lot of natural disasters such as earthquakes can drastically change the landscape. So previous satellite images can basically become unusable in the operation due to the change of landscape. And secondly, a lot of the search and rescue teams conduct grid searches, which is extremely slow and ineffective when it comes to finding a person or finding anything. And and as you can see, a person's life it can be is really fragile and it slow time is time is really precious when it comes to these type of issues. And both of these methods will cause um, plenty of full of resources and also waste a lot of time.
Yeah, to kind of put this in perspective, when we think about grid searches, which is really common for a lot of first responders to use, the way that it's carried out is basically you get a bunch of people. So one, you're already losing a bunch of manpower that could be used for other things. And then you kind of just first make them search in either in rows, like just down rows in whatever sector you're looking at, and then go back and then go in all the columns to kind of get a grid, as the name says. So if you think about that, it's really, really ineffective and it does waste a lot of manpower, a lot of time, and a lot of precious money that could all be used towards helping save people who are in imminent danger a lot faster.
And other people's solutions was to use manned helicopters and drones as well, and as ground personnel to cover the terrain. And as you can see, a lot of manpower can be is wasted. And secondly, another person's solution could be using previous GPS data. And the main problem with using previous GPS data is that there may be a lot of natural changes in the environment which can make render it ineffective into trying to find the missing person and when the person's life is in danger. And thirdly, their solution may be by using search parties consisting of people in large areas of land. And again, it's a waste of manpower and the area they have to cover is really wasteful of time. And our solution is to use autonomous drones to scan an area after the natural disasters to map out an area and create different routes to aid emergency medical services. And our drone is actually a Clover quadcopter, and our drone uses LiDAR in order to map out the environment to quickly and efficiently find missing people in imminent danger in different environments.
Okay, now the way we go about doing these things is first, like Claire mentioned, we do use a Clover quadcopter, which is a pre-made and somewhat pre-designed drone kit that we 3D print. And the reason we do a lot of 3D printing is because it's very cheap and also it's very efficient if we ever need to prototype, which of course we do. And it's very easy to kind of switch out parts quickly when maybe something isn't working or if something might be more efficient. And another thing is that we integrate YOLO with a CNN algorithm for object detection. And now these two things combined, they kind of, what YOLO does is very similar to you only live once, but it's you only look once, which basically means that your camera or your sensor, it takes just a single image of whatever you're wanting to look at, and it processes that and kind of creates different little sectors, sections of that image. And then it kind of brings that over to the CNN algorithm, which takes those sectors of the image and matches it to previous model data that we label to kind of check the probabilities that, oh, this object here might be, say, a tree, or this here might be a car. So it kind of just takes small pieces of an image and matches it to previous data.
So this is image segmentation.
It is image recognition and kind of it just takes with our cameras, we also have to do a lot of flight testing. And then with that testing, we get different images of basically just thousands and tens of thousands of images of just all different things. And then in the background, we would train an ML model to kind of recognize those things over time. So if basically we're just, for example, if there's a tree, we're just telling the computer over and over again that this thing here, this object here is a tree. And then over time, it'll start to recognize that.
Right. So this is classification.
Yes.
Is this classification based on soft voting or hard voting? Like, is it based on probability or prediction?
I believe it's based on probability because I'm not too sure about the core software by this, but I believe it kind of just searches through the our library of data and just kind of matches the current image to the thing that looks basically as close to what it's looking at.
Okay, got you. Thank you.
Yeah. Okay. And then we also use a SLAM algorithm, which is simultaneous localization and mapping, which basically gives the drone or any autonomous vehicle a more, I guess you could say, organized way of searching. So if we take, for example, a Roomba, the way it does it is it's kind of random and it just goes around the room. A lot of Roombas, they just go around the room for a while until everything is clean. But using a SLAM algorithm, instead, it kind of while the drone or autonomous vehicle is moving, it uh, kind of generates an environment around itself and gives itself a location based on that environment so that instead of kind of just going randomly for a set amount of time until the drone flight is stopped, it'll go in the flight in the exact amount of time and space that is needed. And also, of course, as scientists, we love to model things, whether it be graphs or charts or experimentations. Modeling is a very, very effective way to kind of observe anything in science. So the modeling that we do is 3D modeling because we do have a drone, of course. So it's always very good to kind of have a 3D model of our drone see what to see what could possibly be changed, what might not work, what could work. And the specific CAD that we use is Fusion 360, which is just a 3D modeling software and a simulation software. And then we use this to easily visualize where possible components can go in the future. So this could include possible changes to the mechanical design or maybe different electronics that we might want to consider in the future. And we also do a lot of theoretical calculations with CAD analysis tools as a means to kind of double check what we think will happen, or maybe to kind of give us a little bit of a head start to designing something in the future. So for example, one thing that we did is we did add on a LiDAR, which we'll talk about shortly, onto the pre-built drone kit. And then because the drone was designed to have the center of mass in the center by Clover, who made the drone, we wanted to make sure that adding the LiDAR doesn't offset that. So then we would use the Fusion 360 center of mass calculator to kind of double check that the center of mass is still in the center in an optimal location. And now about the LiDAR.
And LiDAR stands for light detection and ranging, and it uses laser pulses to take movements. And by using LiDAR, they use laser pulses and they use it to create 3D maps of an area. So for example, when there is an earthquake that happened, the LiDAR can quickly just scan how the new area looks like. And it uses Python libraries such as Open3D and NumPy and collects the data and creates a map. And it also uses density-based filtering and statistical outlier removal to make the data more clear and quote unquote less noisy.
And then here are just some examples of kind of just test data that we've gotten. The first one is sample point cloud data. So basically it's just sample coordinates of I believe it just was just some random stock environment we found online. And we kind of used backhand LiDAR code to just find a bunch of coordinates of random points on said environment. And then the second example is from taking that data and trying to create a visualization. So taking that data and making it into a map. Because here the top code is basically, well, not code, top data is basically just coordinates with different points in X, Y, Z, then you have some colors and then just some other values. And the bottom takes that data and attempts to make a map of it. And now moving on to the end goals of our project. Of course, because the main goal is to make an efficient drone that can carry out search and rescue operations faster, we of course want both the drone itself and the software behind it to run fast. Because, of course, just common sense, if your system is slow, especially in something like trying to save lives, you're not really gonna get anywhere. And then also, kind of on the same note, it has to be reliable because when the drone is flying, we don't want the data processing to kind of throw back weird, funky values that are inconsistent with what's actually happening because maybe someone needs help in one location and the drone just goes the other way. It's kind of useless. And also, kind of a basic idea is you want the drone to be very cost effective so that it's not really an economic burden on anyone who wants to use it, and that everyone who wants to use it and needs to use it has the ability to do so. And we would like to thank ASDRP for providing us the opportunity and facilities to do research, Dr. McMahon for kind of guiding us and helping us learn how this research should be undertaken in an effective way, and our fellow researchers who have definitely rubbed off on us to kind of point us in the right direction. Thank you.
Does anyone have any questions?